Okay, good morning. It's May 12, 2023. The time is around 2:06 a.m. Good morning. This is Professor David J. De Los Reyes. My topic for this morning will be an interesting one. It will be the so-called derivation of the base of natural logarithm. The value E, the base of the natural logarithm, we will be deriving the value of that using Maclaurin series of expansion. Okay, I will check my camera. Oh, it's fine. Okay, let's proceed. Our topic for this morning will be Advanced Mathematics, lesson number 40. This will be an application of Maclaurin series of expansion in the so-called derivation of the base of natural logarithm, the value E. The value E for natural logarithm is actually, by using the calculator, we could bring out the value of E. Okay, I will bring out the value, then later on I will bring out the derivation and how that value was derived. We will display 1 over here, second function e to the x. The value of e is actually 2.71828, or up to 3 decimal places, it's 2.718. Okay, so by using the calculator, this is the value. Okay, and by using Maclaurin series of expansion, this is the value of e, where e is actually the base of natural logarithm. Okay, let's proceed with the problem. The problem is something like this. Find the Maclaurin's expansion of e to the x, and what is the value when x is equal to 1, okay, up to 3 decimal places. Meaning, derive e to the x by using the Maclaurin series of expansion, and the problem is asking when x is equal to 1, okay, it will be e to the first power, right? Or just simply e. And the problem is asking what is the value. From our solution, it is 2.718, and by using the calculator is 2.718. So the problem is asking for the value 2.718. Okay? For those who are using natural logarithm, the base of the natural logarithm is actually e, right? And the value of e is actually 2.718 up to 3 decimal places. For the common logarithm, the base is 10. That's different story. But for natural logarithm, the value of e is actually 2.718. Okay, let's try to bring out the solution. Function of x will be e to the x. Okay? Take the first derivative. F prime of x will be e to the x times 1, or just simply e to the x. Because the derivative of x with respect to itself is 1, so e to the x times 1 will just be simply e to the x. It doesn't change, right? Second derivative, take the derivative of the first derivative. F double prime of x, meaning the second derivative, will be e to the x times the derivative of x with respect to itself, which is 1, so e to the x times 1 will just be simply e to the x. So as you notice it, we are now on the third derivative, but the right hand side doesn't change. It doesn't change because this is plus. The sign of the exponent of e is actually positive. Okay? Fourth derivative, it will be e to the x again, times 1, or just simply e to the x. Third derivative rather. Fourth derivative, it will still be the same. Just take the derivative of the third derivative, so it will be e to the x times 1, or just simply e to the x. F to the fifth of x, meaning the fifth derivative, it will be the derivative of the fourth derivative, right? So it will be e to the x times 1, or just simply e to the x. So as you notice it, from function of x up to the fifth derivative, the right hand side is are all the same. E to the x, e to the x, e to the x up here. Okay, so there's no problem with that one. That's the so-called differential calculus solution. Okay, let's try to compute f of 0. Because under Maclaurin series of expansion, we needed the values f of 0, f prime of 0 up to a certain derivative, right? So let's proceed. If fx is equal to e to the x, f of 0 will follow this, right? Just substitute the value x to be 0, so it will become e to the 0, and e to the 0 is actually 1. Any number raised to 0 power is 1. So this is 1. Right? F prime of 0, go back to this, substitute x to be 0, it will still be the same. It will be e to 0, and the value is still 1. Second derivative, f double prime of 0, follow this, put the value of x to be 0, what will come out will be e to the 0, and e to the 0 will still be 1. And so with the third derivative, and so with the fourth derivative, and so with the fifth derivative. So these are all 1. Okay, for the derivations, it's all e to the x. Because the multiplier on the exponent is actually the derivative of x with respect to itself is 1. It does not change no matter where you go on the derivative. So these are all e to the x. And for the values, it is all 1, right? Okay, let's proceed. I will check my camera again. Sorry for that one. Okay, let's proceed. Under Maclaurin series of expansion, any function of x will be equal to f of 0, f prime of 0 times x. Okay? F double prime of 0 over 2 factorial times x squared plus f triple prime over 3 factorial times x cubed plus f to the fourth of 0 over 4 factorial times x to the fourth, okay, plus f to the fifth of 0 over 5 factorial times x to the fifth, plus, and so on. Okay, it depends on what function you are taking. Okay, if this is 2, this should be 2. If this is 3, this should be 3. If this is 4, this should be 4. If this is 5, this should be 5. Okay? For the given problem, we will place function of x to be equal to e to the x. That's what the problem is asking, right? It is e to the x. So our function of x is actually e to the x. So if we will follow this, then we will replace function of x by e to the x. E to the x now will be equal to f of 0 is actually 1. This one. F prime of 0 is actually 1 also. So this is 1 times x. This is times x. F double prime of 0, what's the value? It is also 1. All over 2 factorial. 2 factorial is 2 times 1 times x squared. Okay? F triple prime of 0, it is 1. All over 3 factorial. 3 factorial is 3 times 2 times 1 times x cubed. The next one will be f to the fourth of 0. It is also 1. All over 4 factorial. 4 factorial is 4 times 3 times 2 times 1 times x to the fourth. The next one, f to the fifth of 0. Okay? What's f to the fifth of 0? It is also 1. It is 1. All over 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. This should be times x to the fifth. I will add one more. Actually, we could place f to the 6 over here. And this should be equal to still e to the x. And if we get the value of f to the 6 of 0, it will be e to the 0, and that is still 1. Okay, so I will add one more here for the solution to be more accurate, right? So it will be 1 f to the 6 of 0 is 1 all over 6 factorial. 6 times 5 times 4 times 3 times 2 times 1 times x to the 6 plus dot. I think for e to the x, the solution will be accurate up to the 6th derivative. Okay? Because we needed some more digits to the right for it to be more accurate. Unlike the previous problem cosine, we just stop on the fourth one and the actual value of the function now is accurate. But for e to the x, I think it will be more accurate if we reach x to the 6. Okay? So if we try to simplify this one now, therefore e to the x in general, its equivalent under Maclaurin series of expansion will be, this is 1. 1 times x will be x. 1 over 2 factorial is actually 1 half times x squared. 3 factorial is 6, so this is 1 6 x cubed. 4 factorial is actually 24, right? 4 times 3 is 12 times 2 is 24, so this is 1 over 24 x to the 4. Okay? 5 factorial is 120. 120. 5 times 4 times 3 times 2. Is it 120? Yeah, it's 120. So the coefficient of x to the 5th will be 1 over 120 times x to the 5th. And for the x to the 6, it will be 6 factorial. It will be 120 times 6, so it will be 720. 1 over 720 times x to the 6 plus other minimal values already. For e to the x, I think the solution will be now accurate up to x to the 6. We could stop here. Okay? The other values are actually minimal in the effects on the final answer. So, our answer here is the equivalent of e to the x under Maclaurin series of expansion is e to the x in general will be 1 plus x plus 1 half of x squared, 1 6 of x cubed, 1 over 24 of x to the 4, 1 over 120 x to the 5th plus 1 over 720 x to the 6. That's the value of e to the x as a function of Maclaurin's series expansion. It is this. Okay? And the interesting part of the problem is, when x is equal to 1, what will be e? When x is equal to 1, what is e? The value e under advanced mathematics or under higher mathematics is actually the base of the natural logarithm. And actually, if we try to use our calculator, the value of e is 2.718. Okay, let's check if this 2.718 was really 2.718 by using Maclaurin series of expansion. Okay, let's proceed. So when x is equal to 1, by using this expansion here, e to the first power, we set x to equal to 1, right? So e to the first will be equal to 1, plus x, which is 1, plus 1 half times 1 square, plus 1 6 times 1 to the third power, plus 1 over 24 times 1 raised to the fourth power, plus 1 over 120 times 1 raised to the fifth power, plus 1 over 720, I'm following this, times 1 raised to the sixth power. 1 in 1 is actually 2, right? So this is 2. Okay? 1 half times 1 is 0.5. 1 6 is actually 0.167. And 1 over 24 is actually 0.4167. And 1 over 120 is 0.00834. And 1 over 720 is actually 0.00139. Okay? And if we try to take the summation of this, what will come out is 2.718. Okay, you can check it. You should be familiar by using your calculator. There is no problem with this. Okay, we'll do with 1 6 first. 6, take the reciprocal of that, plus open quantity. 1 over 24. You display 24 1 over x, closed quantity equals, we are done with this, plus open quantity 120, 1 over x, closed quantity equals, we are done with this, plus open quantity 720, 1 over x, closed quantity equals, okay? The summation of this is 0.218 up here, 0.218 plus 2.5, okay? So if we try to take the sum, 2 plus 0.5 is 2.5, right? And the summation of this up to this is actually 0.218. So this is 2.718. It is this. So the value of E by using Maclaurin series of expansion up to 3 decimal places is 2.718. And that is the value of the base of the natural logarithm we are using under integral calculus and differential calculus. And to check the validity of our answer, we will use our calculator. We just display 1 over here, the second function e to the x. The value is 2.7182a, or up to 3 decimal places, okay? It is 2.718. Okay? Okay, that's it, guys. That is actually the procedure on how the value of E was computed. So the value of E 2.718, okay, it emanates from advanced mathematics by using Maclaurin's series of expansion. So by deriving this expansion here and substituting the value of x to be equal to 1, what will be the value of E? We take the summation of this after the substitution using this derived equation here. What comes out is E is equal to 2.718. And to check the validity of our answer by using the calculator, up to 3 decimal places, the value of E is actually 2.718. Okay, that's it. So for those of you guys who are taking up advanced mathematics, this is for you. If you want to subscribe to my long form video channel, my channel is at youtube.com/@ProfDavidJ. And if you want to share it, please click share. Okay? This was the derivation of the base of the natural logarithm we are using under differential and integral calculus. Good morning from Los Angeles.